What I will do now, I will first very briefly go through some ideas that were explained last time, and then we move forward. So this is the usual way. We cover something, then return back, cover this again, and go forward. The only thing I have to make sure that we do not repeat the same things over and over again. We have to move forward at some moment. Okay, so as you remember, last time we were talking about the following set of ideas. Before that, we were talking about curves, and curves were assumed to be smooth. And we were able to define some quantities related to the curve in terms of, say, integration and differentiation, in terms of, say, green theorem, and so on. Now we want to get rid of any assumption of smoothness and work entirely with continuous curves. So I must make sure that okay, let gamma be a continuous mapping to R2 without the origin. Continuous, and this mapping is only continuous, nothing else. We want to define, I need to remember, to define what is the change of the angle on this curve about 0. The change of the angle, the curve about 0. Let me remind you something. This is the origin, and imagine we have a small piece, a very short piece of curve. So short that it can be within some cone. Then within this cone we can very well define the notion of the polar angle for all points in this cone. It can be defined continuously, and we can choose, say, the leaf of the angle. Okay, and therefore, for such a curve, we can say what is it? Theta of the end minus theta of the beginning. This is a well-defined notion. But what is even more important is the following. Actually, the notion of the angle is defined not uniquely, but up to adding a multiple of 2 pi. And the angle of this, I can say that this angle is 30 degrees, and I can say that it is the same as how many? 390 degrees. So it's up to me to decide. So each of these angles can be defined in multiple ways, but nevertheless the difference is well defined. No matter which leaf of the angle function we choose, the difference is well defined. So we can do the following. First of all, we split AB into small pieces, choosing T0 equal A less than T1, Tn, which is exactly B. And we can consider gamma I, which is a mapping of Ti plus 1 to R2 minus omega. It is simply the restriction of gamma to Ti plus 1. So that means we split our curve into small pieces. And one can easily show it is possible to split so that each subcurve is in a cone. Well, it is easy. Say it is simply because of compactness of the interval. Lebesgue, or whose theorem? Borel-Lebesgue theorem for an interval. Therefore, well, it is due to uniform continuity. Continuity is the say consequence of the compactness as well. So actually, it is yes.
But I want to emphasize once again why uniform.
Yes. Okay. So what we can do is the following. For each gamma I can define the change of the angle, because each piece is a well-defined. For each piece, this difference is well-defined, as I explained. And actually, I have to sum over I and say that this is gamma of 0. The change of the angle for the whole gamma is the sum of changes. It is by definition. Definitely, the moment you give such a definition, you have to prove several things. Namely, what do you have to prove? That the result does not depend upon how do you split the interval. And second, well, that's the only thing you have to prove. And the result, yes, the result does not depend upon how you split the intervals. The fact that it does not depend, let me put it, theta I, gamma I of ti plus 1 minus theta I of gamma of ti. That is. So there are two choices here. First of all, we choose the splitting of the interval, and secondly, we choose the angle functions in each of the in each cone. Okay, and we need to prove that both choices are irrelevant. So the result is exactly the same. It is easy to actually it is a very easy exercise, and I would strongly suggest that everyone does it in his or her spare time. Okay, but this is something one needs to do. And again, we did not use anything but continuity. We did not need to use, you remember when we did it for smooth curves, we actually were able to define this function on the whole curve by solving a differential equation. But in order to solve differential equation, you have to be sure that the function is differentiable. And we do not have to assume this right now. Just a moment, I must make sure that I do not miss small things. Okay. Actually, we do not have to have, actually, we can consider gamma from AB to R2 minus any point P, and consider the, oh, by the way, too bad. I need to divide by 2 pi. For some reason, I need to divide by 2 pi. And I can consider the, say, the change of the angle of gamma with respect to P. So by simple shift, I can do this.
You divide by 2 pi everywhere, so divide W by 2 pi, is that part of the
okay, I do not divide it here, and I divide it here. Thank you. In particular, if gamma is closed, then W gamma P is integer. If gamma is closed, then this is integer. How can I prove this? Again, let us practice on that. This is not a big deal. This is not a big deal. And it is called W, reminds you that this is called a winding number. Now one small thing more. It is exactly this. If I shift everything by the same vector nu, then nothing changes. All this is translation invariant. Obvious? It is. Now,
It's not so obvious to me.
okay.
You have a path that encloses the origin, and you shift the whole path by it.
By whatever you want. But you also shift the point with respect to which you are computing the, that is important. So actually you simply rename the origin if you wish. It is a question of renaming the origin. Or in other words, a plane is, it remains the same no matter which point in the plane you choose. If you shift in the plane, nothing changes. Okay. Now one small theorem, again we discussed it already, and this is the theorem. Consider a mapping gamma AB times CD, it is a rectangle, to R2 minus say P. And I want this mapping to be continuous. And I assume, okay, everything is here. So let gamma 1, this is, I will draw the picture. This is B, C, D. I take this side, this side, this side, and this side. And these are the directions on this side. Okay? And I can consider, say, what, okay, gamma 1 is gamma of, just a moment, gamma of S of C, I'm sorry, T. So the image of this interval is gamma 1. Gamma 2, I will put gamma 1 here. Gamma 2 is gamma of B, S. The image of this is gamma 2. I put gamma 2 here, though actually gamma 2 is the image of this. Gamma 3 is gamma of what? A, S, gamma 3. And gamma 4 is gamma of T, D. So I will get 4 curves. Gamma 1, gamma 2, gamma 3, and gamma 4. That's what I want to prove about them. And again, it was proven last time, but I need to remind this proof because we will need ideas of this proof. The theorem says, so I'm considering theorem, omega of gamma 1 p, not omega but w, gamma 2p is equal to w of gamma 3p plus gamma 4p. This is what I need to show. So p is any point not in this gamma. And this is true. Then this is true. The idea how to prove it is very simple. Let me split this rectangle into very small subrectangles, so that the image of every subrectangle is in a cone. Can I do this? Because of Borel-Lebesgue, I can do this. So gamma of say rectangle ij is in the cone ij, in its own cone. Say it again.
So P is the point in the image space where you're going to be measuring.
Yes, P is somewhere outside of the image of P is somewhere here.
Okay, so it's irrelevant where the origin.
Yes. Yes, yes. P is, I think I have written it, minus P. P is outside. Okay? And let us do the following. I will take, look, let me put minus here and call it gamma D, gamma capital. Let me put minus here and call it gamma of D, gamma capital. I need to prove that gamma of D, gamma capital is 0. That's what I need to prove. D, not gamma, but dr. R is the rectangle, dr. Okay? So, it's a very bad, actually, I will call it W, I'm sorry. A very bad notation, I'm sorry. I will keep changing notations to prevent audience from falling asleep. If you change notations often enough, it is a very good way of keeping the audience from falling asleep. So I simply call this. dr is the boundary of the rectangle. Yes, the rectangle. No, the rectangle. The rectangle. The mapping is gamma and the rectangle is R. Again, these are the notations are designed to make things as difficult as possible. So claim omega dr is the sum, not omega, w, drij. I will prove this claim in a moment.
All right. So let me follow up on Josh's question. R is the rectangle in the space.
R is the rectangle, is a real rectangle.
So what's the base point you're going to measure the winding angle
With respect to P. First, I have to take by definition, look here.
But you're defining the winding angle.
P's in the boundary of R.
Yes, but the thing is, gamma 1, gamma 2, gamma 3, gamma 4 are already in curves, not the straight lines.
So this is then a definition of the winding angle
Yes,
in
yes.
the original space. But about what point?
Okay, now I understand. The winding number of this plus this minus this plus this with respect to this point. Fine. The thing is, gammas are also written here, but actually gammas are the curves. The curves are the mappings from here to here. From here to here. So I'm writing gamma 1, gamma 2 here and here, but actually the curve is the mapping from this straight line to this curve.
Now, it would be better if he had written W evaluated at gamma of the R.
Okay, but that's how this guy is writing it, and I'm changing.
It's the image of the boundary.
Well, the definition is absolutely correct. There is no question. The whole question arises only. Maybe it can be made more, say, telling than it is. But the thing, let me re-explain it now.
It's just that you haven't told me how to measure a winding number in the original state.
No. I'm not doing that.
Right.
I'm not doing that.
I'm trying to know.
Yes, I understand. The thing is, I take gamma 1, it is the image of the lower straight line under the mapping gamma. I get a curve in R2 minus P. And I measure the change of the angle of this curve with respect to P. That's what I'm measuring. Okay? I'm measuring exactly this quantity. Now I'm measuring the change of the angle of the other curve with respect to P. Third curve, fourth curve, take the difference and call it winding over the boundary of the the rectangle. Did I make yes?
Yeah, the one thing I want to test my understanding, each little rectangle maps into some closed curve in the
Yes.
space, and they share two sides.
Yes.
And
Yes. We will speak about that.
otherwise, there's no overlap.
Yes. Mhm. Okay. This is a claim. Let me leave this claim unproved for a moment, though we actually proved it last time. Okay? And derive the theorem from this claim. Okay. I want to prove that the left-hand side is 0. I will prove that every term in the right-hand side is 0. Which it would, because actually these rectangles are no worse than this rectangle. These are small rectangles. Maybe it is easy to prove it for small rectangles. Correct? But as for the small rectangles, it is really easy. The rectangles are small enough so that the image of the whole rectangle is within a cone. Correct? Is within a cone. So what is this for a small rectangle? This is the angle of the end minus the angle of the beginning, plus the angle of the end minus angle of the beginning, but the end of this is the beginning of this. So they cancel out. It will be the end of gamma 2, the angle of the end of gamma 2 minus the angle of the beginning of gamma 1, which are very well defined for a small rectangle, and that's it. But this is exactly the same. You look at the picture and you see that this is exactly the same. So, omega drij is 0 simply because the angle variable is well defined for a small rectangle. You simply get the differences and that's it. Now why this claim is true, that is the heart of the matter. Why this claim is true? For a very simple reason. Each small curve can be met in two different small rectangles. Correct? And it comes in these two neighboring rectangles in opposite orientations. Correct? Once we get the change of the angle, the angle of this image of this point minus the angle of image of this point, and the other time we get it different. And that's it. So all inner guys come in twice, and they're canceling each other. Is it clear or not? So there are two things. First of all, this is called the additivity of this notion. It is additive. And this is simply because everything is so simple for a small rectangle. Should I explain more? I think that's quite... Okay, now what have I forgotten to say? Nothing. I have not forgotten to say nothing. Now the next point is homotopies. There will be two types of homotopies, though last time I spoke only one type of homotopies. Let me remind the first type of homotopy, which was explained last time, and then I will explain the second type of homotopies. Consider two curves. That means two mappings from the same interval to R to U. Actually, it doesn't matter. U is an open subset of the plane, such that gamma 0 of A equals gamma 1 of A, and gamma 0 of B equals gamma 1 of B. So these two curves have common beginnings and common ends. These two curves are called homotopic, and now I need to add as curves with common ends if there exists a mapping gamma of AB times 0, 1 to U is the same, and the mapping is continuous, such that gamma of T0 is gamma 0, gamma of T1 is gamma 1. So you get these guys, and gamma of AS is the same as gamma naught of A is the same as gamma 1 of A, and gamma of BS is the same as gamma 0 of B, gamma 1 of B for all S. Which means I have two curves, and I'm capable of interpolating between them. I have a whole family of curves between them. So if the parameter of the family is 0, I get one curve. If the parameter is 1, I get another. The only thing I want this mapping to be continuous. Let me immediately define the different notion of homotopy. Homotopy for a different kind of curves. Now gamma naught and gamma 1 are closed. The end coincides with the beginning. I say that gamma naught is homotopically equivalent to gamma 1, and here I need to add homotopically equivalent as closed curves if there exists gamma AB 0, 1 to U such that gamma of T0 is gamma naught. Gamma of T1 is gamma 1, so the same as this. But now I do not have fixed endpoints. So instead of that, I require that gamma of 0s is gamma of 1s for any s. So all intermediate curves are also closed, but I do not require them. For a closed curve, the notion of endpoints is somehow not very well defined. So I better not require anything. So if I have one closed curve and another closed curve, I must be able to interpolate between them, continuously interpolate, to find a whole family of closed curves, continuously depending upon the parameter which interpolates between these two curves. In other words, I must be able to drag one curve so that in the end I get the other curve. And this drag should be continuous. Okay, very good. Now I need to prove a fundamental result, which is actually very easy, which says that the winding number is homotopy invariant. Is homotopy invariant in both cases, for closed curves and for, if the curves are not closed, then I must fix the ends. And for this I only need the theorem I have just proven. And this is the theorem. Let me prove it for, say, fixed ends. Imagine that gamma naught and gamma 1 are homotopically equivalent. That means I have the mapping gamma. Correct? I have the mapping gamma. Then I know that gamma naught, what was called gamma 1 is now gamma naught p plus omega gamma 2 p equals omega gamma 1, what was gamma 3. Gamma 3 was vertical, I'm sorry, gamma 3 p plus w gamma 2 p. Again, to keep everyone alert, I'm changing the notations. Now I call this gamma 2. 4 is now 2. This is, oops, I have a problem. 2 is too much. This is gamma 1. Naught is now, this is 0, this is 1, this is 2, this is 3. Yes, it says gamma 2, gamma 3. Okay. It's very good that we have very many numbers. Enough to change. Well, if we had only 4 numbers, we would have been in trouble right now. Okay. But let us see what do we get. This is what we need. What about these? In this case, they're both zeros. Why? Because of this condition, all points from here go to 1 point. Correct? This curve is 1 point. Because of the conditional of this condition, this is also 1 point. And the change of angle of one point curve is usually 0, no matter how you define it. So these guys cancel out. Not cancel out, but simply disappear. Now, what about this situation? In this situation, these curves are exactly the same. Look here. These curves are exactly the same. And in this case, these guys are not zeros. Each of them is not 0, but they are the same and they cancel out. We did it. So this change of angle is a homotopy invariant. Is a homotopy invariant. What I'm checking is that I have said all necessary words, because it's very easy to Now let me suggest an exercise, but with a hint. Imagine I have a curve AB, U, okay, it doesn't matter. And let phi be a mapping CD AB. Continuous and onto. Not one-to-one, but onto. Then I can consider the composition of these two mappings. It will be a mapping from CD to U. So this is another curve. This is another curve. And this curve is called a reparametrization of the previous curve, for obvious reasons. It is called a reparametrization of the previous curve. Claim if phi of C equals A and phi of D equals B, then the winding number of gamma is the same as the winding number of the reparametrized curve. And if f of C is B and phi of D is A, if it changes the order, then winding number of gamma is minus winding number of gamma phi. Definitely I have to put P, and P is not in U. And I have to put P, I have to put P. Yes?
Should we have P removed from the U in this?
Sure. Otherwise, all these things are not. You see, you do not have to do it here, because for homotopy, it doesn't matter. But when the moment I'm speaking about the winding number, I have to remove this point P. Okay, and the hint I wanted to suggest is the following. This should follow from our main result, from this result. Okay, but actually the thing is that these are there is a homotopy between these two curves, and there is a precise formula for this homotopy, and it is not very difficult to invent it, but I simply put it this way. gamma of AB CD to U. In the first case, it is case number 1. This is case number 2. In the first case, you simply put gamma of T as equal to gamma minimum of two things, T plus phi of S minus A and B. You take minimum of these two. And in the second case, try a bit different. Gamma of maximum, and I think there's T plus, no, yes, T plus phi of S minus B, A. This is a very nice, actually you can prove it with bare hands. It is not a big deal to prove it. But this is a very beautiful proof. So what I'm saying is the following. I suggest that you prove, for example, this result as a consequence of this formula, that this is 0. As a consequence of this formula. But in order to use this formula, you need to invent a mapping of the rectangle into U. And this is the mapping suggested by Fulton. Just check that this mapping is completely satisfies everything you want. For example, if S is 0, what do I get here? If S is 0, T minus A is, if S is not 0, if S is C. Phi of S is A. In this case, phi of C is A. So A minus A. So T is between A and B. So minimum is T. So I get exactly my curve. Correct? Now, if S is D, what do I get here? Phi of D is B. So I have T plus B minus A. T minus A is positive. Correct? T minus A is positive. I have B plus positive and B, which is minimum, B. So in this case, I get a curve which is 1 point. Gamma of B, the curve always sits at one spot. Correct? And definitely, if I have a 1 point curve, then its W is definitely 0. And you get everything from here. We get everything from here. So I would very strongly suggest that everyone spends 5 minutes and does this exercise with this hint. Again, actually you do not need a hint. You can do it straightforward, in a straightforward way, but this is a very natural and beautiful way of doing it. Oh, now at last a theorem. It is called the dog on the leash theorem. And this can be considered to be applied mathematics because it addresses a very urgent real life problem.
Judging by the name, medical biology.
No, maybe even biology. Maybe we should hire someone, a specialist in this area. Let me explain.
Animal Use and Care Committee.
Yes. So, this point is a hydrant. And this is one of us walking a dog. And the dog is on the leash. I'm walking the dog and I hate to have the leash winded around the hydrant. And my question is, how do I avoid this? No, but I can regulate the length of the leash. You see? I can. Well, these leashes are regulated now. Okay. And the result, the theorem is as follows. Let the man go along the path gamma naught, and let the dog go along the path gamma 1. So I have gamma naught and gamma 1. They are moving at the same time. They are in R2 minus the hydrant. They hopefully do not run into the hydrant. Okay? And assume that for any t, for any moment of t, the gamma naught of t, gamma 1 of t, this denotes the straight light segment joining the position of the man and the dog at the moment t. Does not include the hydrant. Then the change of angle for the man with respect to the hydrant is the same as for the dog with respect to the hydrant. So in this case, the leash does not get around there, though it is obvious.
Are you assuming that they are moving on closed curve?
No, any curve. This is a change of angle. You may assume that they're moving in the closed curves. It is up to them. Yes?
So the man stays still and the dog is taking some trajectory.
But the only thing I want that the leash never gets here.
No, but I don't understand the statement. The winding numbers are supposed to be the same for those two curves?
Yes. And they are the same with respect to h, to the hydrant. If I say stay still and the dog runs about me, then my change of argument say my winding number is exactly the same as the dog's. It is 0.
Got to be another condition. The dog starts where it is exactly there, the man stands still, the dog walks to the man and stops. The winding number of the dog
Oh,
changes the
no.
winding number of the man is not.
Yes, I think that, yes. I think they have to be closed.
Oh.
They have to be closed. I'm sorry. Closed. Yes. You're right, absolutely right. These are closed. Let me prove it. And this will be a nice application of mathematics in biology. Not a simple mathematics, but say topology in biology. It is biotopology. Well, it is an interdisciplinary, I would say, result. Okay. I will show that gamma naught is homotopic to gamma 1 as closed curves. Then the result is obvious. And then I have to invent a homotopy. And it is the easiest way to invent. Gamma of t s is gamma naught of t 1 minus s plus s gamma 1 of t. So at the moment t, S will be the point on this segment joining these two, and the relation of this to this is S. This is obviously continuous, and it maps AB times 0, 1 into R2 minus hydrant. Why minus hydrant? This is exactly the condition. All these points are never at H. This is the condition. H does not belong to this segment. Okay? Continuity is obvious. So we've got homotopic equivalence, and that's what we have. So, time to send this off to Journal of Mathematical Biology. Okay, let me jump forward a little bit and immediately prove with all details the fundamental theorem of algebra. And this should be treated as application of biology to math, to fundamental math. Theorem Gauss was the first to prove it. We are not the second, but let us put it this way: the first people to prove it in this room. Would it be a fair assessment? Okay.
Not this building.
Not in this building, but in this room. Maybe. By the way, Ilya, do we prove it anywhere in any class? Yes, in complex analysis it is definitely proven. Mm-hmm. Okay, now let me prove it here. Let P of Z equals Z to the n plus A1 Z to the n minus 1 plus A naught be a polynomial. AI are complex numbers. N is greater than 0.
You have an unusual number.
The sum is O. N. Thank you. Well, actually, I thought this is 0, this is 1, this is 2, this is 3.
Why not?
Well, again, this is a nice way of keeping everyone alert. There exists Z naught in C such that P of Z naught is 0. Proof. Just a moment. It seems, give me one moment, I just want to make sure that I have not missed anything, and it seems I have not. Okay, yes. Assume the opposite. For any Z in C, P of Z is not 0. Then P is a mapping of C into C without 0. We have such a mapping. Take a circle. circle with radius r. Then gamma r will be the mapping of the circle to c minus 0. Simply restrict my mapping on the circle. It is a continuous mapping, no doubt about this. Okay. I can compute the winding number of this. And this winding number should be 0. Why? Because I can take r smaller and smaller and smaller. Okay? They are obviously homotopic to each other. I should not even bother to write the homotopy, correct? And the winding number is homotopy invariant. And definitely when I have a 1 point, the winding number of 1 point curve is 0. So it has to be 0 for any r. Now let me take r to infinity and prove that when r goes to infinity, the winding number is not 0 but n, which are quite different because n is strictly greater than 0. The winding number at infinity is n. How do I do this? I use the dog on the leash theorem. How? Gamma r will be the same as it is restriction of let p naught of z be z to the n. Let it be p naught on CR. This is going to be my dog. And this is going to be myself. Okay? It is easy to compute this. A simple exercise, this is n. You can compute it any way you want. For example, this function is very nice, it is smooth and so on. You can compute the integral or whatever. A homework assignment, compute, prove that this is n. Now, I want to show that gamma r 0 must be equal to gamma r tilde 0 for r large. I will prove it using the dog on the leash theorem. And this is a contradiction because the left hand side is n, the right hand side has to be 0 by our assumption, and the only thing I need to prove is this. I want to apply the dog on the leash theorem. I need to consider gamma r of, say, phi. The parameter along a curve is phi, correct? And gamma r of phi. What is gamma r of phi? It is the polynomial of r e I phi, isn't it? The position, my position at the moment phi. What is gamma r tilde of phi? It is p naught of r e phi. I need to show that this does not contain 0. But I will prove that gamma r of phi minus gamma r of phi is less than gamma r of phi, then it cannot contain 0. If one point, if the length of the leash is less than the distance to the hydrant, then the leash cannot hit the hydrant. This is the length of the leash, and this is the distance from myself to the hydrant. But this is almost obvious, because what is this? I have to subtract this from this. It will be the sum of, Ilya was right, a n minus j, and j is not 0, j is 1 to n, r to the n, r to the n, e I n, not n, j I j phi. When I subtract, the top terms cancel out, and that's what I get. So, and this is, actually I will put it this way, because it is the same. And this is simply r to the n, and this is simply r to the n, because it is the absolute value. It is a simple polynomial, so it is r to the n. But the highest power here is n minus 1.
That's why for j minus 1.
Yes,
What else then minus 1 somewhere else?
n minus 1. Okay, when you will give your talk, I will also find out problems. Okay, but this polynomial is of degree n minus 1 in R. This is of degree n in R, so this is definitely, if R is large, the right-hand side is much bigger than the left-hand side. Proven. So we were quite capable of applying biology to mathematics as well. Just imagine for a moment that we did not have this dog on the leash result. Is everything clear with this proof? Mm-hmm. Very good. Now I need to return back for a moment. Mm-hmm. Mm-hmm. Let me suggest a couple of interesting problems, again for home. And this is important to do problems, because otherwise it does not make a lot of sense going through this book. And some of the problems are really beautiful. Problems, homework problems. I remember there is a good remark in one of books of Mikhail Gromov, one of the maybe best modern geometers. He formulates some conjecture and comments. In the previous edition of my book, this conjecture was exercise number that, and that. After several people pointed out to me that that they could not solve this problem. So in this book, this exercise becomes a conjecture. But he is famous. He is making a lot of conjectures, and there was not a single instance in which his conjecture was proven wrong. So, okay. A simple exercise. U is open rectangle. Prove any two paths in U are homotopic, either closed paths or with fixed, whatever. try to extend it to the case when you use convex, meaning that if you have 2 points and join them by a segment, the segment is still in U. Try to do the same for U star-like. Star-like means there is a point such that, oh, this is not star-like. Take any other point, connect to this one point, and the segment is inside the domain. So it is number 1, it is number 2, number 3. The same thing asked to be proved. So if I have a convex domain, then any 2 curves in this domain are homotopic. What I suggest is that you simply write down the homotopy. For example, if 2 are with common ends, take point gamma 0 of t, gamma 1 of t, connect them. You are sure that you will stay where you are, and simply take the intermediate curve in the same, with the same formula as before. But this simply means that any, say, closed path in the open rectangle is homotopically equivalent to a trivial path, constant path. Because trivial path is a path, correct? And so use this for 3. Use this idea for 3. So in the star-like situation, if you have a curve, simply compress it to the center. That's it. Okay. Another problem. So in this case, I will say that rectangle, convex, and star-like are homotopically trivial. They're homotopically trivial. Everything is the same in them. Another problem is, imagine RU equal R2 minus 1 point. It is not homotopically trivial already, correct? Prove that 2, say, closed curves are homotopic if and only if their winding numbers are the same. So the winding number is a full invariant, homotopic invariant of a curve in the plane without 1 point. We already proved, it follows from what we did, that if 2 curves are homotopic, then their winding numbers are the same. So it is necessary for homotopy, but it is also sufficient in this case. So if you take away 1 point of a plane, it is not going to be, the remaining is not going to be homotopically trivial, but nevertheless what? It is almost homotopically trivial. You have only one condition you need to check. 2 curves are homotopically equivalent if and only if their winding numbers are the same. Again, this is a good exercise and it would be nice. Okay, the last thing I want to say today is the following. And again, we will, for example, the moment we proved the dog on the leash theorem, we immediately were able to apply it to Gauss theorem or fundamental theorem of algebra. And something that I'm going to talk now will be applied to antipode theorem, to the Brouwer theorem, and so on. So this is quite important. One thing more. We consider this gamma is in U and P is not in U. We consider this. We know when this is not going to change. Actually, if gamma is replaced by a homotopic curve, then this is not going to change. The question is, how does this quantity depend upon the change of P. So I will assume that gamma is closed. I assume that gamma is closed. Let support of gamma be the set of gamma of t between A and B. So the support is the curve itself without any parameterization. The support is the curve as the geometric object without any parameterization. Gamma is closed, therefore support is something like this. Correct? So U minus support, by the way, let's say R2 minus support gamma consists of several components. Correct? Consists of several components. And one component is unbounded. There's one component outside. Theorem. W gamma P is constant in P on every component of what? R2 minus support gamma. And omega gamma of P is 0 on the unbounded component. The last part is easy. If I am far away, then definitely the winding number is 0 because it is in a segment. Correct? How do I prove it? Quite easy. Take any component and take the point P1 in the component. In order to prove that this function is constant in the component, I must only prove that it is locally constant. I must prove that the function is locally constant. Any locally constant function is constant on every component. Okay? Surround this point by a small disk centered at this point and take any other point P2 here. I need to prove that the winding number of gamma with respect to P1 is the same as the winding number of gamma with respect to P2. It is what I need to prove. And it is easy because I can write that this is the same as gamma with respect P2 plus P1 minus P2. Correct? Addition of points as addition of vectors, if you wish, or complex numbers. Which is the same as gamma plus P1 minus P1 minus P2. P2. You remember I said that I can shift everything. Let me shift both sides by this vector backwards. Okay? And the only thing I need to prove that this is true. Then everything is going to be correct. So I want to prove that gamma is, this is closed, is homotopically equivalent to gamma minus nu. Nu is this vector. And again, it is not a big deal to do this. You can simply write down the homotopy, and that's what I want everyone to do. The small exercise is find the homotopy. But actually, it is the same kind of linear homotopy, which is very easy. You must move along nu. That means gamma s is gamma minus nu s. If s is 0, I get gamma. If s is 1, I get this. And definitely these are simply the same curves, but shifting. Okay? And they are not going to hit the point P2. Okay, we will need this. So I'm sorry this was about, say, 1/2 of today's talk, but it took a bit longer than I expected. I hoped that today I will be able to prove the theorem about the existence of a fixed point. Yes?
You need convexity if you want density or...
No, I do not. The thing, actually what I need convexity of this small ball, which is convex.
To show that's in the domain no matter what, doesn't the domain have to be convex or so?
No, the thing is, again, I need to prove that all these curves do not hit P2. You see? But come on, nu is so small that I can always ensure this. Just let me show you one small thing. It is really, consider interval AB and a continuous mapping of this interval into itself. Then there exists continuous x in AB such that f of x is x. So any continuous mapping of a segment into itself has a fixed point. I will prove it in just one picture. A, B. A, B. They belong to this line, correct? Let me draw the graph of this function. It starts on this line, f of a is something, and finishes on this line, f of b is something. And then it has to intersect the diagonal, and this is exactly x. This is x. Actually, I will prove this it is possible to prove it in any dimension. Okay, and this is called the Brouwer theorem.
Any need to define a contraction mapping?
There is a retraction mapping. We will define retraction map and prove that under some conditions some sets are not their own retracts. But again, this is just a matter of it quite easy. But actually a lot of integral equations, differential equations, nonlinear especially, they boil down to a good fixed point theorem. When you are solving a differential equation, you can almost always say nonlinear. Almost always you can reduce it to an equation of the existence of a fixed point, but unfortunately in the infinite dimensional space. So the Brouwer theorem itself does not work in the infinite dimensional space, but there is a wonderful extension called Schauder theorem. Schauder, who else? The Schauder maybe theorem, which says that under some conditions, weakly compact, say, convex sets in say Banach space, they do have this fixed point property. And a lot of differential equations fall within this result. Okay, so are we ready to continue? So we continue as long as we are being fed, I believe, right? Okay, thank you, and I'm sorry that I did not have a chance to do more.